Okay, Mike. So to get started a little bit, a few things. One, as a reminder, on Friday, there are going to be, so the related rates homework assignments are both due on Friday. And as a suggestion, a strong suggestion is do not wait until Friday evening to try those problems. Not that you would like to spend Friday evening doing math anyway. Well, maybe I should, if you like to spend your Fridays doing math, that's great. But if you just want to get the homework done, the problems take a long time. Like if you think about the examples we saw, they're not the kind where you just take a derivative and you're done. So you really want to make sure you give yourself enough time, either working on them today or tomorrow, so you have time to get questions answered from me, or kind of consult your notes and other examples a little bit more. And you don't want to be trying to just scramble to do these difficult problems Friday night. Also, what I'm going to do, unless there's really, really strong opposition to this, is that I had said our second exam, so originally scheduled for this week, I pushed it back. But looking at the schedule, the day that you have to, the last day for withdrawing is from a class is next Friday. And so to ensure that everyone at least has taken the exam before that, what I'm going to do is have the exams be next Wednesday and next Friday, rather than next Friday and the following Monday. So if you have a strong negative reaction to that, send me an email and I'll kind of take it under consideration. But I would rather everyone sort of have an idea of, have a better idea of where they're at in the course, instead of having some people take the exam after the withdrawal deadline. And for that, this afternoon, I'm going to be putting up practice exams so you can start to take a look at those as you study for the exam. And I'll put in an announcement on Canvas all of this so it's written down with dates and details. But I just want to let you know that the next exam for part of the class is going to be in a week, and then the Friday after. So what we're talking about now is one of the big applications of calculus, and this is about finding maximum and minimum values of functions. And there will really be two different types of maximums and minimums that we're going to talk about. They're going to definitely be related, but that's why I'm being I'll be a little perhaps pedantic in laying out exactly what I mean by some of these words. So first up, let a point C be in the domain, whatever it is, D, of some function f. Then the height f of C is the absolute maximum, or these are pretty parallel definitions, absolute minimum, if for every other point x in this domain D, in the maximum case, you are the biggest value. So that means that f of C is greater than or equal to f of x. In the minimum case, you turn the inequality around and you're the smallest. F of C is less than or equal to f of x for all x, which is what you would expect. The maximum is the biggest your function gets anywhere where it's defined. The minimum is the lowest value that it gets. And there's a small distinction here to keep in mind between where the maximum or minimum happens, that's the x, or the input C, and the output f of C is the maximum, that's the highest high or the lowest low. So for example, if we say here's some function on the interval 0 to 6, we could say this is something like here, and then it's high, and then it's low, and then it's up there again. So given this function, it's, let me make this a little clearer what's happening. So then in this case, the absolute maximum, the highest value that we get on this interval is up here. The lowest value that we get is down here. So the absolute maximum of whatever the height is at 6, and the absolute minimum of whatever the height is down there at 2. One thing that we'll also think some about is if we look at these 2 points that I'm circling here, this point at 4 and this point at 5, those aren't the highest high or the lowest low. But at least they're definitive high points and low points for the graph. They're not the highest high, but this is a definite peak. And this isn't the lowest low, but it's a definite dip. So we'll come back to talking about how, or we'll also be interested in points like this, which aren't the highest or lowest, but are still these sort of definitive high and low points. So talking about absolute maxes and mins, we'll want to think about how to find them. And before we actually get to the process of finding them, we're going to want to think about what the possible answers to that question. What are the absolute maxes and mins? Because there's some subtlety to what sorts of possibilities there are. In this case, this is the most straightforward. There's one, here's the maximum, there's the minimum, and that's all there is to say. But what if we look at this example? Cosine on the interval 0 to 2 pi. So cosine has this wave shape going between 1 and -1. So cosine starts up at 1, then it's 0, and then it's -1, and it's 0 again, and then it's up at 1. So its graph has roughly this shape. And in this case, we can ask what's the absolute maximum and minimum? And here there's a kind of small wrinkle, which is a little peculiar. Because in this case, if we say what's the absolute minimum? Well, we have our low point down here. That's the bottom of the dip that happens at pi. So there's the absolute minimum of -1 at x equals pi. Keeping it straight, the minimum is the value, the height, and then it happens at a particular x. What's strange though is the absolute maximum, if we ask that question, well, it gets up to 1, and that's the highest that it gets, but it actually gets up to that height twice. So there's an absolute maximum of 1, but it happens at x equals 0 and x equals 2 pi. So what is happening here is there can only be one highest high, but that highest high can happen at different places in the graph. And not only can a maximum happen more than once, but possibly there might not be a maximum at all. So if we think about x squared on everything, well, x squared is our good old parabola. And in this case, our vertex at the bottom is definitely our minimum. So there's an absolute minimum of 0 at 0. So you input 0 and that lowest point is 0. But if you're looking for a maximum, well, it just keeps going up. You're allowed to keep using as much space to left or right as you want. And so there's no absolute maximum, which can happen. Another situation, which is maybe even a little stranger, is what if we look at e to the x on that same interval, looking for all real numbers. So e to the x, think about its graph. The exponential function goes off to infinity to the right, and it's going down to 0 off to the left. So in this case, actually, there is no absolute extrema at all. Extrema is the catch-all word for maxes or mins. And the fact that there's no maximum is kind of believable. It keeps going up, so it doesn't stop. What's a little stranger is that this doesn't have a minimum, even though there's this horizontal asymptote at 0, so it never gets below 0. So there's like a lower bound for how low it can go. But what happens is it keeps getting smaller and smaller, and it never makes it to zero, but you can keep going further and further left, and the output value is getting smaller and smaller and closer to zero. So a minimum is there's an input that gives you that lowest value. There's an input that gives us 0, an input that gives us -1. There's no input that gives us 0 for e to the x. But for any input, especially if you go out to the left, you can go further left and get even lower. Clarifying questions about any of these examples. So this isn't really to show you anything new. It's a little bit to talk about, or talk using this terminology of maxes and mins, but also this is meant to say, we need to think sort of carefully about this. How do we know? Well, there are two big questions we need to talk about. When are there maxes and mins? Because there are cases where we don't have them. And then how do we find them? How we'll find them is actually by backing up a little bit and thinking about how would you find these kinds of points. So these points aren't the highest or lowest, but they are high points and low points within the graph of the function. So this is going to look very similar. And I'll keep this graph up here. So we'll take C be in the domain of the function, and we'll change the definition that was absolute maxes and mins here to f of C is a local maximum, or alternatively a minimum, if f of C is greater than or equal to a of x, or the minimum case, f of C is less than or equal to f of x for all x close to C. Where close, if you want to be a little more precise, is saying in a small interval around the point C. But at least on the graph, the way that we can think about this is I drew these little circles, and if you only looked at x's that put you inside that circle, the top of this point that we get by putting in 3, that's the highest our function gets. It's not the highest anywhere, but kind of zooming in and looking locally, it is the highest point. And the same thing down here. It's not the lowest point our function gets anywhere, but if you only look in a really narrow range close to that input, it is the lowest point that you can get there. So this point up here, this is a local max. This is a local min. And this blue circle happening at 2, this is a local minimum. And it also happens to be the absolute minimum. These endpoints, we don't really think of them as local maxes and mins, because it could just be that we happen to cut it off here, and if I didn't cut it off, it would keep going up. So endpoints are sort of a strange case. what's even a little bit stranger is that as we've seen here, we can have a bunch of maximums and minimums at a bunch of different points. We could even do something like, so if here's some kind of wavy looking function, well, this has a bunch of local extrema. It has a max and a min and a maximum and a minimum. And what's a little strange to say is this local maximum or this local minimum is bigger than this local maximum. So being a local extrema doesn't really have any relation to other points. It's just right in this area, I'm the biggest that the function gets. So these local maxes and mins, they tell us about certain features of the graph, but they'll also be important because these will be easier to find where they happen. And we'll use that to talk about or to help us figure out absolute maxes and mins. So right now, there are maybe there are a lot of questions. But two big questions are, one, how can you be sure in a given situation that there is an absolute maximum and minimum? Because we saw some examples where we had functions that didn't have absolute maxes and mins at all. So that's one thing we'll want to know. What kind of situations can we be sure that these maxes and mins exist? Because we'd like to know that they're there before we go looking for them. The second thing is, even if you know they're there, how do you find them? And finding them is where a lot of the work that we're going to do will show up. But we'll also want to think about in what situations is it reasonable to ask for a maxes and mins. So today, as has been what's going on to this point today, today is a lot of laying the sort of groundwork for understanding these concepts. And I'm not sure if we'll get into a lot of what the problems look like. So we're going to be trying to understand these maxes and mins and figure out when they exist, how do you find them? And it might not be until Friday that we really get to, okay, what do the problems that we actually do look like? Which makes it kind of a tough day, but it'll be worth it. So this first question. When do absolute maxes and mins exist? So the statement which says when we can be sure that they exist is what's called the extreme value theorem. And what this says is that if you have a function f of x and it is continuous on a closed interval AB, then there are points C and D in your interval. So f of C is an absolute maximum, and f of D is an absolute minimum. So what this is saying is really the situation where you know there are going to be these maxes and mins that we'll have to figure out how to look for, but we know they're there, is that your function is continuous and you have an interval that's closed. This on its own doesn't say anything about how you would find them. That's going to have to come next. But what is worth pointing out is that this combination is really the right one. You can't be sure of maxes and mins existing if you don't have both of those. So for instance, one thing that we've already seen is you need a finite interval. So we said if we look at x squared on minus infinity to infinity, well, that's our standard parabola. And this has no maximum, which is maybe not surprising. If you have sort of infinitely many room, you can keep going up or keep going down. But in fact, even just finite isn't enough. You really need the closed part too. So you need a closed interval. So let's look at x squared again, but on the open interval 0 to 1. So what is this graph going to look like? Well, it's part of a parabola. Our parabola goes from 0 up to 1, but in this case, we're not allowing 0 and 1 as inputs. So we have a hole down here because we're not putting in 0, and we'd have a hole up here because we're not putting in 1. And so what's happening here is a little like that e to the x example. As you go in this way, as you put in x's closer and closer to 0, the outputs get closer and closer to 0, but because you don't have that endpoint, you never actually make it to 0. So there's no minimum because you could keep picking smaller and smaller x's that make your f of x smaller and smaller too. And then the same thing on the other side. If you keep picking your x's closer and closer to 1, the outputs get closer and closer to height 1, but because you don't have that endpoint, they can just keep going up, filling the space between kind of where you are and 1. So we really need those endpoints to say you can't just creep up. You really have to stop at these endpoints. But we also, even if we have a closed interval, we also need continuance. So we need continuity. Because if we look, for instance, on 1 over x, 1 over x on the interval, say -1 to 1. The problem is this function has an asymptote at 0, and that's what's going to not give us a maximum and minimum. So 1 over x. At 1, our function is at 1. At -1, it's at -1, but then it has an asymptote. And so because we keep going up, we don't have a maximum there. And because we keep going down from the left, we don't have a minimum there. So this is all to say, this situation, if you know you're continuous and the interval is closed, you're going to get maxes and mins. If you don't have any part of that, then you might have a maximum and minimum, but you can't be sure. So in a lot of problems, we're going to be looking at functions which are continuous and we have a finite closed interval. And so when we ask for maxes and mins, we know that we're going to find them. Or we know that we're able to find them. We'll just have to actually do it. Questions about these examples, which isn't really a problem, but it's just saying this is the context we're going to look at, because beyond that, we just can't be sure that we have maxes and mins. So now for the more practical question of how do we find these things? And it'll take a little bit to get you exactly the right way of looking at it. But I don't want to just throw it at you and say, this is what it is. I want to kind of work through why this is the right thing to look for when we actually do some kind of problem. So question 2 is, how do you find absolute extrema? Even if you know they exist, just their existence doesn't help. So the first idea, which helps us get there, is this statement, which is called Fermat's theorem. So this is Fermat, it's French. If you know any French, well, if you don't know French, you basically don't pronounce the back half of words. So this is Fermat, not Fermat. He was a lawyer, but he also was a mathematician in his free time. And he essentially figured out how you can use calculus to do these kind of application problems in like the 1500s. So what this theorem says is that if a function f has a local maximum or minimum at a point C, and if the function you're looking at is differentiable at C, then the derivative at C is equal to 0. So this is part of why all those questions about horizontal tangent lines, really why those were kind of a repeated theme. Not because horizontal tangent lines are so interesting, but basically that work is going to be a big part of how you find maxes and mins. So this is, in this statement, it's important to understand what this says. What this is saying is that if you have a maximum or minimum, then the derivative is going to be 0. And so if there's any chance for a point to be a maximum or minimum, the derivative has to be 0. But we can't kind of turn this around. So I want to have 2 warnings. Well, I guess first let me draw a picture. So what this is saying is kind of familiar. If we look at this sort of example that I saw before, this has a bunch of maxes and mins, and all of them are horizontal tangent lines. And in all of these examples, if you looked at every example where we found horizontal tangent lines and graphed that, you'd see a lot of maxes and mins. But we need to be careful. So here's the first one. And this is that just because the derivative at a point is 0, this doesn't imply a maximum or minimum. So in a sense, there can be false positives. What this is saying is that you want to find maxes and mins, check where the derivative is 0. But there can be cases where the derivative is 0 that aren't actually maxes and mins. For example, we don't have to search anything too exotic. An example that works is, what if we look at x cubed? Let's find where the derivative of this is 0. So first up, power rule. That brings the 3 down. The new exponent is 2. We get 3x squared. Set this thing equal to 0. Divide by 3, take a square root. You get x equals 0. So x cubed does have a horizontal tangent line at x equals 0. But if we look at the graph of this, we don't actually get a maximum or minimum. Because what x cubed looks like is it's going up, it flattens out at 0. So we do see what we expected. There is a horizontal tangent line here, but it flattens out, but then it keeps going up again. And so it's not like these cases where you go up, you're flat, and then you go down, giving you a maximum. Or you flip that, go down, flatten, go up, giving you a minimum. So this is one thing we need to watch out for. Just because you find a place where the derivative is 0, that doesn't mean you have a maximum or minimum. The other warning is that the derivative being 0 isn't the only thing that can happen at maximums and minimums. So we'll say extrema can happen even if, well, I won't be like coy about it, can happen if the derivative doesn't exist. So what this theorem says is that if you have a maximum or minimum and you're differentiable, so if you have a derivative there, the derivative has to be 0. Well, what if you're not differentiable? That's an option 2. And so, for example, we can say, what happens if we look at the absolute value function? So the graph of this is this v starting at 0. And looking at this graph, we have this corner right here at 0. And one thing which is clear from the graph is this is the absolute minimum. We keep going up the other directions. So there's a local minimum at x equals 0. But what we also know is because the absolute value has that sharp corner, it doesn't have a derivative. So f prime of 0 doesn't exist. Questions about either of these warnings here? What they're what they're saying and what information we want to take away from them. Okay. So what we can do now is really, we've seen a lot of stuff. We can summarize it into the way that we'll actually think about things going forward. And we'll start with this definition, which will basically be, these are the points you have to worry about if you're trying to find maxes and mins. So we'll say that a critical point, or sorry, a critical number, sometimes called critical point, So a critical number of some function f is a number c in the domain of f. So the derivative of c, the derivative of the function at c is 0, or the derivative at c doesn't exist. So these critical numbers are the points you have to worry about for maxes and mins. Well, first of all, it has to be in the domain, because you can, if you're not in the domain, you're definitely not a maximal derivative. But also, what this theorem and these examples indicate is if you're going to be a maximum or minimum, the options are your derivative is 0, or maybe your derivative doesn't exist. And then we'll say a fact summarizing the situation is that if a function f has a local maximum or minimum, local max or minimum at a point c, then c is a critical number. So these critical numbers are the ones which will help us find maxes and mins. But the wrinkle in all of this is essentially we have this warning 1, which says, but, exclamation point, not every critical number is a maximum or minimum. So what we'll have to do is, if we want to find maxes and mins, step 1 is find all the critical points. But then we somehow are going to have to figure out which of these are maxes, which of them are mins, and which, if any, are these sort of false positives. And what will turn out to be the way that we go forward is determining which ones are maxes or local maxes or mins is a little harder than actually finding the absolute maximums and minimums. But just to break things up a little bit, this says a new question you can get asked is, here's a function, find all its critical points. And although that's some new terminology, it's really similar to work that we've done before, especially if you think that this is not exactly, but pretty close to, find the horizontal and vertical tangent lines of a function. because horizontal tangent lines are where the derivative is 0. Vertical tangent lines are where the derivative has an asymptote, and that corresponds to non-existing, but C is in the domain of the original function. So while there's new terminology, the work is familiar, which can help us assimilate this new stuff into what we've already been doing. So for instance, what if we said, let's find all critical numbers of this function. F of x is x cubed minus 3x squared minus 6x plus 3. And although there's this new terminology, a critical number is where the derivative is 0 or doesn't exist. So step 1 is take the derivative. And this certainly we can differentiate. It's a bunch of power rule. So f prime of x is the 3 comes down here to get the 3x squared. The 2 comes down here to give us 6x. Then we keep the minus 6 there. The plus 3 is a constant, so that has derivative 0. So this is our derivative. In this case, it's a polynomial, so we aren't going to have to worry about this derivative not existing. And that's something that happens. If you have maybe a logarithm or a fraction is the most common thing here, you have to worry about the derivative not existing. But now we can say we want critical numbers. All we have to do is set this thing equal to 0. 3x squared minus 6x minus 6 is 0. And now solve this quadratic. To make things a little easier, all of these have are multiples of 3. So we can divide everything by 3. That gives us x squared minus 2x minus 2 equals 0. And solving this, this one turns out to not factor, which happens. Like last time on the exams will have the quadratic formula, which you will always need, but I'm not testing you on if you have the quadratic formula. So that looks like opposite of b, that's 2 plus or minus the square root of b squared, so negative 2 squared, minus 4 times a, that's the 1 in front of this x squared, c, which is the negative 2, all divided by 2a, so 2 times 1. If you simplify the inside, that turns out to be 12. So we get 2 plus or minus the square root of 12 over 2. One thing that's important to understand when you use the quadratic formula like this is that there are two numbers here. There's 2 plus the square root of 12 over 2 and 2 minus the square root of 12 over 2. So these are places where this graph has horizontal tangent lines. One thing we don't know yet is if these are maximums or minimums, or if they're like x cubed where we level off, but then we keep going under. So that question we're going to come back to. Given a function like this, you found these critical points. How do you tell what kind of local extrema these are, maxes or mins or neither? What actually turns out to be a little bit easier is using what we know about these critical numbers in order to find absolute maxes of things. So we won't get into an example, but I can lay out the way that we're going to think about it. So absolute maximum and minimums of continuous functions on closed intervals. So one thing we know is that the extreme value theorem that we mentioned before, extreme value theorem, says they exist. So we know in this situation that they're going to be out there. We just have to find them. If we're looking for them, one thing we know is that inside the interval, they have to be at critical numbers. So if you have a maximum or minimum inside your interval, then it actually has to be also a local maximum. It has to be a real high point or low point of your function. But then also what it could be is maybe your function was going up and you just cut it off somewhere. And that's where your maximum turns out to be. So the other option is they could be at the endpoints. So what we'll do, and we'll see an example of this next time, which doesn't seem very sophisticated, is say, well, just find all the critical points and add to that the endpoints of the interval and see where the function is the biggest. What you basically get is when you find the critical points and also include the endpoints, is you have these are the options for where my function could be at its maximum or minimum. And if you know it's one of these, just check which one's the biggest. And the biggest number that you check is the maximum. The smallest number that you look at, or that you get as an output, is the minimum. So where we'll pick up is actually doing a problem where we find the absolute maximum and minimum, but this is the idea behind it. Critical points and endpoints are the options, so just test them to see where the max and minimum. Okay, so that's where we'll pick up next time. I will see you guys. Bye.